Hey y'all, Data Guy here. And today I wanted to make a video for y'all just kind of breaking down some of the most common terms used when talking about machine learning. And the reason why I want to do this is because, I'm finding myself using these a lot. And it's really kind of underscored to me how much people use them just as like a way to sound smart when they're actually not that complicated in practice. And so what I want to do for you today is I'm going to take some of the probably about the 10 most common kind of machine learning terms that I hear thrown around a lot, explain what they mean to you, kind of how you do them, just so that next time someone tries to big brain you, talk down to you with all these fancy words, you know what they're talking about. You can say, hey, chump, shut your mouth. And if you like this kind of video, please like and subscribe. And if you want to go further in machine learning after this, check out any of my other videos on the topic. So without further ado, let's jump into it. And the first one I wanted to cover is, hey, what is an algorithm? And you can think of algorithms as just like the basic logic behind decision making. So let's say, a good example of this is Netflix, right? So Netflix will understand that, hey, this user is watching videos about science fiction. So an algorithm that it's using that's taking in your data, on a regular basis, every time you load up the Netflix app, it'll say, hey, find movies that are similar to science fiction movies and serve them to George. And then that algorithm will say, hey, we'll go search through all the videos, find the ones that are most similar to the ones that I enjoy, and then serve them to me. So that is really what algorithms are, at their most basic level. They are just a set of steps to take an input and produce some output based on that input. So they're not as kind of everyone always says, oh, the algorithms are going to rule us all. No, algorithms are just a basic set, kind of a data pipeline, if you will, taking one state and using it to produce an outcome. And so it doesn't even have to be like really complicated machine learning. This could be something, just like some data analysis. But as algorithms get more complex, Netflix uses machine learning to process all the data, find the correlations to give you the best movies. But at its most basic, it can be something very simple. And so the second topic I'd also like to discuss are neural networks. So neural networks are basically a series of data points. So a hidden layer, this would have algorithms governing how data points are related, where, you're processing a large realm of user interaction data. Maybe a common instance of this is Google image recognition, and that's because neural networks will mimic the human brain structure. So in that kind of Google image recognition example, when you upload a photo, Google will then say, hey, here are some objects or the Google neural network will say, hey, here's some objects within that photo. So imagine you're in the Google, Google Maps car driving around. It's classifying, oh, this is a fire hydrant, this is a house, this is an address, and then can find, similar shapes, can find, the Chinese government's using it to identify, people that are passing through certain places. And neural networks allow you to do that because they're able to process so many data points at the same time versus just like iterating through every data point within a single picture could take way too long. And so building on top of that is deep learning. And so what deep learning is it's layers and layers of neural networks. It is algorithms that only really work well when they're processed on just immense amounts of data. What does that mean in the real world? Autonomous vehicles. So imagine, your car is driving around and it has to interpret so many different variables around its environment. And imagine, if you're a driver, you're a human brain, you're processing that. So neural networks are simulating that. And with deep learning, you'll have layers and layers of that. So camera capture video is processed through layers that detect objects, that interpret traffic signals, then makes driving decisions based on all those inputs. And so that's where deep learning comes into play, because you have models that get more performant as you get more data and are able to accommodate those just massive, massive amounts of data. And that kind of brings me to my next two terms, which I'm going to show you together because they are pretty related to that. They're like almost opposites of each other. And that is supervised and unsupervised learning. And so in supervised learning, the model will learn from labeled examples. So for instance, in this example, spam filters, it's a classic use case. And so supervised models will be trained on emails that are labeled either spam or not spam, and then use the patterns found in those emails to read any further emails and identify them. Hey, do they match something that I've already seen in spam or not spam? And so to contrast that, unsupervised learning relies on models that can learn from and act on unlabeled data. And so algorithms can identify hidden patterns without any guidance. And so this is great when you're saying, hey, maybe I don't know any patterns that I can recognize in this data, but maybe this algorithm will. And so like something like that would be market basket analysis and shopping. Customers who bought this also bought others. And that's where you rely on an ML model to say, hey, track all these different customer interactions and find who is buying, what other items are they buying most likely or most commonly for people that have bought this existing model. And then we also have reinforcement learning. And so in reinforcement learning, it's a type of ML where an algorithm learns to make decisions by trial and error. And that typically involves human in the loop engineering. And so it improves the performance based on its outcomes. So your agent will produce some reaction. In this case, it's going to be, hey, my model produces an outcome. I have a testing environment that's going to say whether this is the correct or incorrect thing to do. And then its result is kind of fed back into the agent to say, hey, this was the right thing to do, or this was the wrong thing to do. And then the agent knows that and is trained from that. So it knows, hey, it knows whatever action that was, it was either the right thing to do or the wrong thing to do in that situation. And so it either will or won't recommend it in the future. And so this is a great, thing where, hey, you expect a lot of trial and error. And if it's not a human in the loop, then it can be, something like this where it's conditional logic. But human in the loop, for anyone who doesn't know, is when you have someone that's reviewing the results of an ML model manually as part of this process. So the environment would be a user, and then telling the agent, hey, that was wrong or that was right. And you can also have this like in chatbots where ChatGPT, hey, says, was this useful or not? That's essentially what's happening here. And so the next term I get thrown out that gets kind of crucial for really any machine learning model is feature engineering. And that is the process of identifying the features or the predictor variables. So the variables that you want to use to predict your ultimate outcome. So an example of this would be, say, hey, I want to predict someone's credit score. And so the features that I would use to predict that would be things like, hey, what's their average, what's the most time, or how often are they paying their credit card bills on time? Do they have any outstanding loans? What do they have, any missed rent payments, et cetera, et cetera. And then the feature engineering would be deciding, hey, out of all the different data points about a person's life, what's your most relevant and will give me the best result in terms of predicting their credit score. So feature engineering is the process of identifying, hey, these are the variables that are most highly correlated with whatever my ultimate goal target value is. And so it helps you identify those and then have a model that is trained to just use those to predict your ultimate value. So you get the most accurate answers. And so here we have this lovely floral graph for my next point, which is overfitting. And so overfitting is when it's modeling error that occurs when you have a function that's too closely aligned to a limited set of data points. And this typically occurs when a model learns the detail and the noise in the training data to the extent that it negatively impacts the performance on new data. So essentially, because the training data set is so small, it is only attuned to the different relationships between the data within that particular training data set, rather than the broader correlation on the of let's say, and I guess to explain this, I'll use an example because this will make it a lot simpler. Is a stock prediction model. So maybe it works perfectly on past data, but it fails miserably on future data because it becomes so tightly designed to predict for that subset of data that it was trained on. And this is because, maybe the model became too complex. There was too many local variables that were included that were actually only correlated to that particular moment in time. And so when you try to use it into the future, it falls apart. And so that's when you got to go back to the drawing board, figure out what happened. And then bringing us home in the home stretch, I have our last two, and you'll notice the classification and clustering. And you notice that these are very similar to unsupervised and supervised learning because they are very similar, in fact. And so clustering is a method of unsupervised learning. It's kind of a subset that involves grouping sets of data with similar characteristics. So while you might not be perfectly categorizing each sets of data like you would be in supervised learning, you say, hey, all the children, I want to analyze them separately from all the adults because they have different characteristics in terms of, you know, their correlation between height and weight. And so this allows them to find, you know, structures for that specific group rather than trying to find a correlation on the entire population of children and adults, where each of those distinct groups can kind of throw each other off. And then on the flip side, you have classification, well, not even the flip side, but just kind of a different way of doing it. And so this is where you will actually use an algorithm to categorize your given set of data into different classes. So this is where, even though, you know, you might, let's say you don't know who's an adult and who's a child in this data set, classification would allow you to feed that data into a classification algorithm, and it would separate that data into different categories. And so what this, you know, an example of this in the real world is like, let's say, hey, I have medical diagnoses where instead of children and adults, I have people with diseases or without, and classification goes through, or would go through there, find the people with diseases, and classify them into two different groups, you know, healthy and non-healthy. So they're kind of just two different roads to the same objective. And so classification goes more for that supervised learning because, you know, you're really defining that specific class or like set of characteristics that you want to be to assign that data into its particular group. Versus clustering is kind of loosely coupling all you know, data points with similar characteristics. And so I really hope that you, you know, found some value in this video, that you got inspired or now have enough understanding of how machine learning works and all the different buzzwords for you to go out there and impress everyone at your holiday party this year. So without further ado, have a great rest of your day. Data Guy signing off. Peace.